Right now, as you are watching this, seismometers positioned along the Himalayan arc are logging what scientists at the National Seismological Center of Nepal and the USGS Earthquake Hazards Program are describing as an anomalous continuation pattern. The rupture sequence that opened beneath the Nepal-China border has not followed the expected decay curve. The data stream coming out of those instruments is showing something that monitoring teams have learned to treat with acute seriousness: spatial migration. The aftershock zone is not sitting still, it is moving. The new earthquakes are not clustering tightly around the original rupture plane the way standard aftershock sequences do. They are advancing along the fault. And that specific pattern, migration rather than contraction, propagation rather than decay, is the signal that geophysicists use when they describe a fault that has not finished releasing. The word confirmed in the title of this video is doing real work. Scientists do not use that word loosely when describing behavior along one of the most heavily loaded tectonic boundaries on the surface of this planet. What they have confirmed is that the rupture energy is still moving, that the fault system has not returned to its pre-event state, that the stress which is being redistributed by this sequence is following a directional path along the Main Himalayan Thrust toward a segment of that fault that has not produced a great earthquake since 1934. What is coming is not a certainty. But the instruments are not showing a quieting system. They are showing a system under continued mechanical stress, with the leading edge of that stress propagating toward the most hazardous unruptured gap in the entire Himalayan arc. Before we go into what that means for the tens of millions of people who live above and downstream of this fault system, you need to understand what we are actually talking about when we say the Nepal-China border ruptured, and why the phrase "not stopping" has a precise scientific meaning that is more alarming than the casual language of breaking news tends to convey. If you find this kind of analysis valuable, the real science, the verified data, the actual numbers, make sure you are subscribed and have notifications enabled, because coverage of this event is going to evolve quickly, and we will be updating as the monitoring data comes in. The Himalayan mountain range exists because of a collision that started approximately 50 million years ago and has not stopped for a single day. The Indian Plate, the section of the Earth's lithosphere that carries the Indian subcontinent, is driving northward into the Eurasian Plate at a rate that modern GPS satellite networks measure at approximately 40 to 50 millimeters per year. That is roughly the same rate your fingernails grow. It does not sound catastrophic. But over geological time, and with the mass and rigidity of a continental plate behind it, that convergence rate has produced the tallest mountain range on Earth and has loaded the fault system beneath it with stored elastic energy that dwarfs the output of any human-made energy source. The fault where that energy accumulates is called the Main Himalayan Thrust. The Main Himalayan Thrust is a gently north-dipping megathrust fault that underlies the full length of the Himalayan front, a continuous structural feature stretching more than 2,400 kilometers from Pakistan in the west to Myanmar in the east. It is not a vertical crack in the crust. It is a shallow angle ramp, dipping into the Earth at roughly 10 to 15 degrees, which means the fault surface that generates Himalayan earthquakes extends deep beneath the Tibetan Plateau on the Chinese side of the border and shallow beneath the mountain front on the Nepalese side. The Nepal-China border runs directly across the surface expression of this system. The fault does not respect the political line. The peaks of the Mahalangur Himalaya, the high passes of the Tibetan Plateau, the river gorges that cut southward into Nepal, all of it sits on the hanging wall of a fault that has been storing energy for 9 decades without a full release. What makes the current sequence scientifically significant is what it is not doing. In a normal aftershock sequence, the pattern of seismicity following a major rupture follows what is called the Omori-Utsu law, a mathematical relationship that describes how aftershock rates decay over time in a predictable power law curve. Under that model, the first hours and days produce the highest rates of aftershock activity. Then the rate falls. The spatial distribution of aftershocks tightens around the original rupture zone. The fault settles. The system moves toward a new quasi-stable state. This pattern is well documented across thousands of earthquake sequences globally, and it is what seismologists look for as evidence that a fault has returned to a mechanical state of relative stability. The sequence along the Nepal-China border is not showing that pattern. The seismic rate is not declining at the Omori-Utsu pace. And more significantly, the spatial distribution of new events is not contracting. It is migrating along the fault plane in the direction that seismologists describe as a long strike propagation, the same direction as the unruptured central Himalayan segment. What this combination of signals, anomalous rate, migrating distribution, a long strike directionality, describes is a fault rupture that is still advancing. The mechanism is called Coulomb stress transfer. When a fault ruptures, the elastic energy that was stored in the surrounding rocks does not simply disappear, it redistributes. Some goes downward into the mantle, some goes toward the surface, and a measurable quantity of it travels horizontally along the fault, loading the adjacent locked section. The calculation of how much Coulomb stress has been transferred along the Nepal-China border segment is being actively computed by research teams at the USGS, at GFZ Potsdam, and at the Institut de Physique du Globe de Paris. What those calculations will confirm, and what the spatial migration pattern already suggests, is that the next segment of the Main Himalayan Thrust is receiving stress. Not releasing it, receiving it. To understand why that has the monitoring community paying close attention, you need to look at the contrast case. The reference event for everything we know about large Himalayan earthquakes is the Gorkha earthquake of April 25, 2015. That event reached a magnitude of 7.8. It ruptured a section of the Main Himalayan Thrust approximately 140 kilometers long in the east-west direction. The slip on the fault plane was estimated at 5 to 6 meters over the rupture area. More than 9,000 people were killed. Hundreds of thousands of structures were destroyed. The world watched Kathmandu Valley, which sits approximately 70 kilometers southeast of the Gorkha rupture zone, sustain damage that cost Nepal an estimated $10 billion, roughly half of the country's annual GDP at the time. The Gorkha earthquake was large, but it was not the event the seismological community had been anticipating when they analyzed the accumulated strain across the central Himalayan seismic gap. The gap itself is defined by the boundaries of the two most recent Great Himalayan earthquakes on either side of Nepal, the 1905 Kangra earthquake to the west at magnitude 7.8, and the 1950 Assam earthquake to the east at magnitude 8.6, one of the 10 largest earthquakes ever recorded instrumentally. Between those two events lies the central Himalayan segment, and for that segment, the last great rupture occurred on January 15, 1934. The Bihar-Nepal earthquake of 1934 reached a magnitude of approximately 8.2. It killed somewhere between 10,000 and 30,000 people, destroyed much of the architecture of the Kathmandu Valley, and reset the strain clock on a portion of the fault. That was 90 years ago. At 40 to 50 millimeters of convergence per year, 90 years of unresolved strain represents 3.5 to 4.5 meters of accumulated elastic deformation. Energy locked in rock, waiting for a fault surface to slip. Published estimates of the full rupture potential for the central Himalayan gap, including work from research teams at the University of Colorado, Caltech, and the Indian Institute of Technology, consistently return moment magnitude estimates in the range of 8.5 or greater for a full rupture of the gap. The Gorkha earthquake did not clear that bill. Post-event geodetic analysis using GPS networks and INSAR satellite data showed that the Gorkha rupture slip occurred at depth, in the mid-crustal portion of the Main Himalayan Thrust, while the updip section, the portion closest to the surface, the section that generates the strongest ground shaking in the near-fault region, remained locked. The strain transferred from 2015 did not release the gap. It partially loaded adjacent segments, and the Nepal-China border section of the fault was among those that received a positive Coulomb stress increase from the Gorkha event. The current rupture propagation is running on top of that inherited stress. It is not starting from a neutral baseline. It is adding mechanical load to a segment of the Main Himalayan Thrust that has been in a state of Coulomb stress elevated hazard since 2015, carrying the accumulated strain of 90 years of unresolved convergence, with the updip section of the fault still locked. That is the context inside which the phrase, "the next wave is already moving," belongs. The secondary hazard cascade from a major seismic event in the Nepal-China border zone extends far beyond the immediate shaking damage, and the scale of that cascade is specific to this region's geography in ways that distinguish it from other megathrust systems. The high-altitude terrain above the fault system is the source environment for some of the most dangerous glacial lake systems in Asia. Glacial lake outburst floods, GLOFs, occur when a glacial lake impounded behind a moraine dam fails suddenly. The moraine dams that hold these lakes are composed of glacial debris, unconsolidated rock, ice, and sediment. They are not engineered structures. They are geological accidents that formed as glaciers retreated. and they are precisely the kind of structure that strong seismic shaking destabilizes with extreme rapidity. Satellite monitoring data from the International Center for Integrated Mountain Development, the ICIMOD, based in Kathmandu, has documented a dramatic expansion in the number and volume of high-altitude glacial lakes in the Nepal-China border region over the past 3 decades. As Himalayan glaciers have retreated under warmer temperatures, they have left behind growing lakes behind unstable moraine barriers. A major earthquake on the Nepal-China border segment would simultaneously shake a landscape containing hundreds of these lakes at elevations ranging from 4,000 to 5,500 meters, above river valleys populated by communities with no viable evacuation route and no early warning system capable of providing meaningful lead time before a GLOF arrives. The river systems that drain southward from the Nepal-China border, the Koshi, the Gandaki, the Karnali, and the Mahakali, are the primary water sources for a combined downstream population in Nepal, India, and Bangladesh, numbering in the hundreds of millions. These rivers are already carrying elevated sediment loads from ongoing glacial retreat. A major earthquake, GLOF, cascade in the headwater zone would transform these river systems in ways that the downstream communities are not prepared for, and the infrastructure along those rivers, bridges, irrigation systems, flood control embankments, is not designed to survive. The monitoring infrastructure in the Himalayan region, while significantly improved since 2015, remains less dense than what exists along the Pacific Rim. The National Seismological Center of Nepal operates a national seismic network, and the USGS Earthquake Hazards Program publishes a continuously updated global earthquake catalog at earthquake.usgs.gov. For the Nepal-China border specifically, the most current hazard assessments are generated by teams that include the USGS Geologic Hazards Science Center, GeoHazards International, and the GFZ German Research Center for Geosciences. The published seismicity maps, Coulomb stress change calculations, and ground-shaking hazard models for this region are available in open-access scientific literature and are updated as new data comes in from the ongoing sequence. Kathmandu Valley sits approximately 70 to 150 kilometers from the segment of the Main Himalayan Thrust that is currently propagating. Its 3.5 million residents live on a geological substrate, the sediments of an ancient lake that filled the valley before the Bagmati River carved its way through the surrounding hills, that is among the most seismically amplifying soil types on Earth. Lake sediments, saturated with groundwater, respond to seismic waves the way a bowl of gelatin responds to a tap. They amplify and prolong the shaking far beyond what bedrock at the same distance would experience. The 2015 earthquake, with its rupture zone centered 70 kilometers northwest of Kathmandu, caused buildings in the valley to sway for 60 seconds or more. A rupture closer to the Nepal-China border, on the up-dip section of the fault that 2015 left locked, would produce a ground motion in Kathmandu Valley that the existing building stock has not been tested against. The Earth does not release energy on a schedule that accommodates human planning. The Main Himalayan Thrust has been loading for 50 million years, and the Central Himalayan Seismic Gap has been accumulating strain since the winter of 1934. What is different about 2026 is that we have the instruments to watch what is happening along the fault in real time, and what those instruments are confirming is not reassuring. The rupture is still propagating. The spatial migration of seismicity is still tracking toward the locked segment. The stress inherited from 2015, added to 90 years of pre-existing strain, is now being supplemented by the stress transfer from the current sequence. These are measured facts. They are not projections or models or probabilistic estimates. They are what the seismographs are reading right now. What we do with that information, how seriously the international community invests in monitoring and preparedness infrastructure in the Himalayan region, how transparently the science of the seismic gap is shared with the communities who sit above it, how honestly the risk is communicated to a world that tends to pay attention only after the shaking has already stopped, is not a geological question. It is a human one. The next wave is already moving. The window to prepare is not infinite, and the instruments watching this fault have given us something rare, the signal before the silence that precedes the rupture.